Now you can see that even though the first two samples are of different values originally, but because they are falling under the same sample, both of them will be assigned the same fixed value, which is the fixed value of the first level. So let's say the fixed value of the first level is x1. For the second level, the fixed value is x2. For the third level, fixed value is x3. And like this, for the last level, fixed value is x8. In that case, if you observe carefully, the first two samples, because they fall under the first level, will be assigned the same values of x1, x1. And hence, even though they were originally different from each other, the difference is no more recorded at the output of quantizer because they fall in the same level. Hence, like sampling, quantization is also a lossy process. We make sure that the loss of information is less by having very small size of the level. In that case, it will be only two close samples. The two samples with very close values will be falling in the same level. Two samples with the values which will have some good difference between them will fall in the different levels and hence will be assigned different values. If you look at the third and the fourth sample, they are also falling in the same second level, so both of them will be assigned the second fixed value, which is x2, x2. So we are done with the first, second, third, fourth sample. Fifth and sixth sample are also falling in the same third level, so you assign the value of x3, x3 and so on. Last few samples, if you observe carefully, the last two samples are falling in the last level that we have, so they'll be assigned the value of x8, x8, and before that the previous sample may have the value of x7. Now because we are using 8 different levels and 3 different bits for each fixed value, from x1 to x8 we may have the representation in the form of ones and zeros. For example, x1 may be represented as 0, 0, 0, x2 may be represented as 0, 0, 1, and likewise x8 may be represented as 1, 1, 1. So when I say the first two samples are given the fixed values of x1, x1, they are basically represented with 3 zeros. x2, which is the value representing second, third and fourth levels, will be simply written as 0, 0, 1. So in the process of quantization, we assign the discrete sample values some fixed values based on the levels in which they fall, and every fixed value is then represented in the form of ones and zeros. How logic 1 will be represented, how logic 0 will be represented is decided by the type of encoder that we are using. In simplest of forms, logic 1 can be plus 5 volts and logic 0 can be minus 5 volts, or logic 1 can be plus 5 volts and logic 0 can be 0 volts, and so on. Now if you observe carefully, there exists some error in the quantization process. As you can see, the first value, the first sample value is not exactly falling on the red line, even though we are assigning it a value which is represented by the fixed value of this red line. So you can see there is always a difference between the actual value and the quantized value of the samples. This difference will be maximum if any sample falls at the border of the two levels. So let's say if the sample is here, in that case you may assign it a fixed value represented by the third level. In that case, the total maximum error will be nothing but half of the total size of the level. The size of the level is called step size, which we can represent using letter delta, and hence the quantization error that can take place, the maximum quantization error will be always step size by 2, which is delta by 2. We can find corresponding quantization power, which will represent the noise power that is taking place in the quantization, and based on the signal power of the original signal and the quantization noise power, we define something called as signal to quantization noise ratio. It is very important that we keep signal to quantization noise ratio values as high as possible, because it's nothing but the signal power divided by the quantization noise power. If the SNR values are very low, that means the quantization noise is very large. We can always reduce the quantization noise by reducing the quantization error, and to reduce the quantization error we must reduce the step size. Now if you observe carefully, the size of every level is nothing but the total range VH minus VL, divided by the number of levels in which we are dividing the total amplitude level. So to reduce the step size, we must have maximum number of levels possible, because if m is large, delta will be less. And if you increase the number of levels, that means you have to increase the number of bits that you are using in the process of quantization. So the simple conclusion is, to increase the SNR value, we'll have to increase the number of bits also. With increased number of bits, the bit rate will increase, and that will also require us to use greater bandwidth for the transmission of the signal. And hence, there should always be trade-off between the SNR and the bandwidth requirements of the signal transmission.